Welcome to another talk by the San Francisco Bay Area IEEE PELS group. Due to the low contrast on the video, I've pasted in the slides, but you can also find them on our website. We're also skipping the intro and starting on slide 2.
And was the power plants in one side and the consumers in the other side. Then this one provides that the power flow from the production to the consumption. But then the voltage profile was very simple. You have the voltage going down with the losses of the line. But now appear solar and wind farms that throw to the system more excitement. Together with the old generations is what we call microgrid. But now create a new paradigm that is a distributed system, and then the profile of the voltage get all messed up. In addition to that, the houses are beginning to have small grids, small microgrids, that is exactly the same resemblance of the big microgrid, but just in a smaller scale. And then that one is not a standard for the IEEE, but many people begin to call that one nanogrids for the residential, below 100 kilowatts, and for the commercial, and for the residential below 25 kilowatts. That one is very interesting in rural and in cities, like we will say later. Then this new paradigm have disadvantages and advantages, like everything in life, everything in engineering. That is the reason we are in engineering, right? We have more complex technologies. Probably because we have more complex technologies, probably will be more expensive. You lose the control. The power utilities, the power generation have the control all the time. Now everybody begin to have some control. And then because everybody can mess up the system, probably we will have less reliability. And then we don't know how to deal with that. Then we will need new regulations. And then probably we will have power quality issues. But at the same time, every problem has a potential solutions and potential opportunities. That one will be better used to the local resources. We don't have to transfer power from one side to another one. Then the consumers will have more independence. And because you generate some of the power, you will have some piece of the cake or have the potential. We can be environmental friendlier because we have the source of the power very close by. And even more important, because can be less reliable, but in the other hand can be more reliable too, because the destruction of the central power or some power plant now allow you to be, because you have your own power generation, allow you to be able to survive in case of hurricanes or cybersecurity attack. And believe it or not, maybe have some economically possibilities too. MIT make that study in one part of India that they have 400,000 people with no electricity. Then the options was go with the power line that you have, the low power, and extend it to the houses that don't have power. Create standalone systems for that village, or create small microgrids in different situations. The surprise was, probably if they asked me, probably I will ask for the first. Then the solution was more complex like that. That was more complex because reality sometimes surprises you. Then different locations create different solutions. Then the most economical solution was all of the above. Was not a single. Then now that we know nanogrid has some possibilities, let's study the characteristics of nanogrids. Nanogrids, they can be tight grid. That means they can be connected to the grid. And then if they are connected to the grid, they borrow from the grid frequency, and they borrow the voltage. You don't have control of that. You have to follow that. In the other hand, you have the ability to have that one detachment from the grid, and then we call it landing. The perfect nanogrid, or the best desirable nanogrid, is one that can do both. Then you have to have a transfer switch that allow you to go in any of the two situations. When you are tied to the grid, you are exposed to the tariff. And now there are consumption by the day. You can, the kilowatt hour that you consume at 2 p.m. or 3 p.m. could be way more expensive than what you consume at 4 a.m., for example. And then in that scenario, you become like the ability to buy stocks in the market, because you can buy when you consider low and you can sell when you consider high. Then provide you some independence, because you cannot necessarily be only dependent of the grid, like we talked before. Germany, for example, that is leading in that area, unfortunately don't have too much sun. Then probably they can go only 60%. In the United States, we are more lucky in that sense. Many areas, Arizona, Southern California, they can provide enough energy to be 100% independent. Then, again, the nanogrid that is connected to the grid then have fixed voltage and fixed frequency that is dictated from the grid. Then if we have a low-cost transfer switch, we can deal with the islanding. In islanding, you are not connected to the grid. Then the power that you generate has to be exactly equal to the power that you consume. Then you have to generate your own frequency, your own voltage, and then you have all the controls in stability that was referred to us in the book. Then you have to get a little bit of that, and you have to control the generation. In addition, you have to order and classify your loads by criticality. You have to say that one is essential, that one is not essential, and then you have to manage that the criticality from priorities. And then usually, and most probable, you will have power quality issues. When I mean power quality in power system, typically is flicker, sag, and swell. What is flicker, sag, and swell? Then flickers is when they have intermittent light, and then this one was developed in a way to simulate 5 tons in a house. When the air conditioning starts, they consume a lot of current. And then in my former company, when I was working for Sonnen, we developed this small system to simulate the star. And you can see how the voltage drop. And when they come back, you have a voltage swell. Then that one will be typical in a system that you have in the backup mode. Then there are two schools of thoughts in nanogrids. Some people want to go DC, some people want to go AC. Virginia Tech is a big proponent of the DC. What is DC? Even in DC, there are other classifications. There are the possibility that you go with 12 volts. Some people call the 12-volt or 24-volt picogrid, because we are beginning, and that one is typically in third world countries that they have to charge the cell phone and many basic situations. Then you get 12 volts only for these functions. But the DC is more efficient than AC, and it's more easy to control. The only reason AC was the dominant, and Edison lost the battle to Westinghouse and Tesla at that moment, was because we didn't have power electronics at the time. The inverter was very difficult. And then, but now we have power electronics, but we are like 100 some years later, and then we have already infrastructure. Then to change the infrastructure to DC is complicated and expensive. Then DC have these disadvantages because you have to change the whole products that you buy to be DC coupled. Then the AC, in other ways, is easy to retrofit. You don't have to change anything. You use what you have. The disadvantages, like we will see, is more difficult to see the control, and it's region dependent. If you are in Europe, you have 50 hertz. You are United States, you have 60 hertz. Mexico, 60 hertz. But then the system that works in Europe don't work directly in United States. Then let's go in more detail. What is the DC nanogrid? The DC nanogrid, you make the couple. That one is the basic definition. It's more complex than that. Then you have, for example, a PV panel. Then you have the batteries. You usually need a bidirectional DC-DC converter. Why bidirectional? You need to recharge the battery and discharge the battery. And in the PV panel, it's unidirectional. Then you don't need a bidirectional inverter, but because you have the battery, this one has to be bidirectional. And after that, you couple to the AC grid. In the AC grid, you have your PV panel. This inverter is unidirectional because always the power goes from the PV panel to the grid. But then you need another inverter that is bidirectional, but you go and you connect that one directly here. You can have that system earlier, and then you come back and you put the battery later. Let's go in more details about the DC nanogrid. Typical DC nanogrid right now is a standard to 380. It's 380 because that one is the proper voltage that produces 240. And then, because that one is very close to the typical DC bus in the inverters, they decide to get the 380. And then Virginia Tech was working a lot of in that standard, and then I think everybody else follow, and then we have that 380 right now. And then you connect everything directly to the 380. The old generators can be connected to DC, you rectify, or you can connect it to the AC. You need one bidirectional inverters, and for some circuits can be bidirectional, other one can be unidirectional. And then the people proposing that nanogrid, still they believe all the devices in the house have to be DC. I don't believe that, and I think still we will have a legacy system that still will be AC for long time. The DC have a huge advantages because there are no anything more simple than control power in DC. Because power in DC is voltage times current. Then if you want to generate, for example, if you want to regulate the power that you are getting from here to here, only you use what is called droop control. Then you put the power that you want to get the most to a higher voltage level. And then you will use that voltage level. When you begin to demand more power, the voltage will drop to a point that you consider state 2. And then at that moment, the generator that you don't want to produce power, but you need it now because your voltage collapse, will hold the power enough for a long time. Like you see, droop control in voltage is extremely simple. Then, well, not that simple, but it's a basic control by levels. You put levels and then that one will do it. In the AC microgrid, then you have that one is the typical house that you have right now. You have the washer, dryer, sometimes the dryers are gas, but let's say that they are electrical for the sake of the conversation. You have the AC unit, you have all the loads, and then typically you have the inverter here that connected to the grid. You can have the wind power directly connected, or you can have an inverter there. You can have a gas generator, and now you need the energy storage to be the master controller. Take the energy that you are producing in excess in the wrong time of the day and keep it for when you need it later. And then you need to communication with the cloud, know how it's going to be tomorrow. And then you need a transfer switch, like we talk, when you are going to be in this stage or when you are going to be just connected from the grid. The Druck control becomes way more complex. That complex that people have been talking about, then in addition, you have to evaluate the loads, why you don't care in a specific moment, then maybe you don't care about TV, then you don't care to do washer and dryers in sometimes, or you don't care about lining depending if you are during day. And you need, when you are generating too much power that you cannot dump in your batteries anymore because your batteries are full or your storage are full, you need to dump the energy because you remember, power in has to be equal to power out. If not, you lose the system. The Druck control, because we are in power electronics, I decided to go a little bit deep in that, not too much. Then you have the typical power system relation that you have angle, you change the angle, then the current flow from the load. Then this one is a typical applied to a solar inverter or a battery. Then you will have, this one is the impedance. That one is the connection between the inverter and the grid. Why that is important? Because there are a lot of studies about control and they talk about universal control. Typically, the inverter, this system is morely inductive. Then that one means the typical inverter is what is called L inverter. Then anyway, we are going to mention that because can be, but basically we are going to concentrate in the L inverter. That one will be inductive, like it is in any power system, and all the questions are derived from that system. Then, when in general case, then you have the impedance in general, but in a typical power system, this angle is very low, then you assume 0, and we assume inductive, you can get this type of rules. P is the real power, Q is the inductive power, that is only the power that you need to storage sometimes in the process back and forth. It's like energy, accumulated energy. Then knowing the power and knowing the Q that you need in your system, and using this equation, you can know how you are going to control your system. Then Dr. Song, I think now he's in Indiana Institute of Technology, he created the generalized control, and this one is a publication, you can find it, it's available to everybody. And then I will just do a little bit of the favor to see with this particular control, with P and Q, and how you control the Q, that is the reactive power, and how you control the P. Then it's very simple if you follow the table that he proposed. You have voltage, you have current, that one generate Q and P. Can be, that one can be a DQ transformation. We won't go in that. Then in that case, he said that one will be negative, that one will be positive. And then if you want to control the reactive power, you control the voltage that you generate. If you want to control the power, you control the speed, the frequency that you generate. Like I said, AC systems are way more complicated than the DC, even in that simple, simplified system. Then let's talk about the battery storage. The battery storage or the energy storage can be many shapes and forms. Can be air compression, hydraulic, thermal. We are going to concentrate in capacitors and batteries. even though there are many alternatives. But in order to limit this talk, why you need batteries and capacitors? Because it has to be very fast. Remember, we have to balance the power, and we need, like in inverter, you need the DC link that can be capacitors, but in a house, the capacitor storage, the ability in the capacitor is very limited. Then we need a little bit more capacity. Then we have sources that they are intermittent, like the sun and the wind. We have generators that we can control, but they are using soils. They're using liquid to work, fuels. And then there are problems not only associated with the environment. There are problems that you have to have that gas or whatever delivered to your home. And sometimes it's complicated. You have a farm far away, it's difficult to provide that element. Then you can have other types to accumulate energy, like air, for example. They are very ingenious way. And then the easy way is use a battery. And then you use the inverter like we talked. But in this case, you are disconnected. Always the power has to be constant. Then in the capacitors, we have nowadays ultra capacitors that some people use in combination with batteries. We are not going to go in details too much. That one are faster even. They can provide very fast response. But the batteries usually are extremely good in providing the response associated to that. In batteries, I am going to talk, typically before was lead acid, is the battery that we more know, it's associated to the cars. We have a nickel cadmium was very popular for a long time. And now we are going to go, I will go directly to the chase, we are going to go to lithium ion. What most people don't know, there are three very distinct lithium ion batteries. Cobalt, that is used by Tesla, mainly, and all the car manufacturers. And then they have a lot of power. The density is very good, and then you have to move the car, then it's important the high density. That one, like everything in life, has some disadvantages. They can blow, and they can get fired very easy. Lithium-ion manganese are cheaper, and that one are in the cell phones. That one is the pack. Anybody open, that one come in like in a bag. And right now, when I was working in Sonnen, then lithium iron phosphate was the big promise. We will see why. Didn't happen that go that way, but the promise was that the battery prices have been going down significantly. These one are comparisons, 2014, and you can see like lithium ion was very close to lead acid. I don't think ever we were thinking that one happened. And lithium iron phosphide, why was so important? Because it's made from iron. Lithium is somewhat rare, but it's not so rare. Then the iron and phosphate, you see, are extremely abundant. Then the people in the area compare with cobalt, for example, that is somewhat rare. Manganese is very common, but even lead is somewhat rare. And even though it's somewhat rare, lead is extremely cheap compared because the industrialization create that. Then there are no any reason why lithium iron phosphate cannot be even way cheaper than lead. Well, there are one reason. When the people realize that that one will have a value in itself, then they begin to jack the price up, like it always happens with something, happened with the permanent magnet motors. There are many cases, but theoretically, they can go very low price. Supercapacitors, they are way lower price supercapacitors. Everybody's offering, all the manufacturers offering supercapacitors, but they don't have the possibility to store energy in enough quantity. Then batteries the price still are going down, not at the rate that we wish, but go down, but the main problem is they have the life that is somewhat limited. How many cycles you can get from the life. Then there are a lot of research associated to that. This is the typical examples how you model the battery. It's very simple, very similar to that. And then, but more important is how the capacity go down depending on the charge, depending on the temperature. Every manufacturer, 1, 2, 3, was the first to create the first iron phosphate battery. And then in the cars, 7 years is pretty good. That one is what you expect from a Tesla or from a Leaf. But for a home, you want that the stuff lasts 15 years. You don't want to be changing the batteries. Then iron phosphate is very promised in that sense, lasting way more than manganese and cobalt. And then there are a lot of research associated how the aging of the batteries, how we can evaluate that. And then, but all boil down that you begin to do more cycles. The real part begin to increase. That one means the losses are beginning to increase. Then we know for the standard temperature, I don't want to go in too many details, when the losses begin to grow, we have deterioration of the battery. Then, like I said, why the battery is important for the nanogrid? Because we have, for example, solar. Don't have to be solar, but you have the extra energy during the day, and then probably you will need it at night, and then you will like to have the dosification of that. But even if you don't have batteries, you have a peak demand that the utility charge you for the peak demand, even if you don't have solar, I mean. Then you want to storage energy when you have the peak demand to avoid to get the price that the utility is going to charge you because you are asking for energy in the wrong time. Then if you have batteries, you can overcome that. Then batteries, they have different rate of charge or discharge. Then again, can be very complicated because not only that, if one battery said, I am 1C, and then you charge it to 2C, you will charge the voltage very quickly, but the charge that you put in that battery is way lower than you charge it to 1C. Not only in charge and discharge, and the rate of charge and discharge, but have to do with the temperature too. Then probably the battery need to accommodate temperatures too, and knowing that the rate of charge is 80% of the rate of discharge, that one create the minimum size of the battery that you need for the system. This is an example how the batteries for homes are coming. They are make like that one looks like a small batteries, make it in panels. There are thousands of them created. That one is 2 kilowatt-hour system. Then we very quickly we went to the batteries. Let's go to the inverters. I hope this part is more interesting for power electronics. Then we have all these articles that come in the 2015 about all the inverters that appear. Thank you to the evolution of the inverters. But there are 3 classifications very quickly. Low frequency with transformer, that was the first. High frequency and transformerless. Transformerless is what could provide best price and best size for the power that you can get. Then Very simple. That one is the low frequency transformer. That one is one example of the high frequency, and that one is one transformerless inverter. Let's go with the bidirectional inverter, because the only difference between a battery storage and the solar is that that one has to be bidirectional. They have to take energy from the grid and take it that. That is the most simple system that you can have. Only drawback, you need a transformer that works with the frequency. What is the frequency? The frequency of the grid. That one means bulky, huge transformers. There are tricks. Then you can do interleaving steps in frequency to create a transformer, a shape sinusoidal with interleaving. Or you can go further and create the transformations here at high frequency. You have the battery here, you have one inverter here, the other inverter that in the solar was only the diode because you need the rectification, and this one is very high frequency. Now you have the same inverter, but the transformer was moved from the front to here. Very small transformer. These one are examples of soft switching. Vicor create a low price DC-DC converter with soft switching. Then let's go and put a little bit, talk about the difference that there are between transformerless and high frequency. The efficiency can go very high with the transformerless, and the size and the weight is very high. That is the tendency. That one is an example of a transformerless inverter. Then these transformerless inverter, for example, usually are 3 levels inverters, and then everything is basically box connected with different switches. Then you can do steps. Then, for example, this one is the type I, and this one is the type T. And then in both of the cases, that one will be the positive buck, and that one will be the negative buck to create the voltage. And then you have switches to control when one operates and when the other operates. When you need to be bidirectional, then now the grid, you create like you create a converter that creates energy, and you transform that energy to the coil, and after that you close that device, you open that device, and the energy go in the direction that you want, opposite to the grid. This one is a transformerless DC-DC converter. And then when you do transformerless inverter, you have other issues, because you have to avoid that the current that go to ground in order to take the standards is less, for example, depending on the size of the inverter, in this case, is less than 1 ampere. Then you have to make all the simulations proper to verify that the currents that go to ground are below 1 ampere. You are creating inverters of 25 kilowatts, but they can go up to 5 amperes for bigger inverters. But then you have to avoid that the path to ground are high enough. And this one is very interesting inverter. This one is an inverter that was proposed, Ideal Power come out. This one is not a voltage inverter like the other one. That one is, the transformation go to the inductance. That one is called, this one was, Princeton Power was the first to explore this idea. Then the idea is you have this coil here, and then you have a DC that is the battery. The battery produces a current that charges this inductance. This inductance, now you move it to the AC. And the beauty of this one is when the inductance was here, because the inductance always take the voltage of the source, because they are voltage agnostic. Now that he's connected to the AC, now they took the voltage of the AC and deliver the current. Then, if you charge again that inductance, and now you want to go to the opposite current, you take the other connections and you connect it backwards, and now you create the current in the other direction. Then you transfer the energy in a beautiful way. And the problem is they are very expensive. They are different inverters. Still the people consider that. And they have some other issues. This one is a three-phase model of that inverter, explaining in details what I just tried to make. They have the capacitor only to create a loop when it's not connecting to any place, because as you know, the step before oversimplify, because you cannot disconnect in inductance with current inside. Then you put a capacitor, and this capacitor is a concern of reliability, because this system have to, when you disconnect the inductance, the current have to keep there. The control is complicated. This one is a typical control for a inverter connected to the grid. These one are possibilities of control, and then possibilities of the control for a standalone. And this one is a little bit more interesting, yet, because you need to know the type of load that you have, but then you have to have a GUI, and you have to have a control, the node, your production, your consumption, when you charge and when you discharge. And knowing that one actually is a real GUI. That one was a real place working in a real fashion. Then you can see when it's discharging, when it's charging, when the PV is producing, and the consumption. And more important, because you are connected to the grid, you will know this one are actual voltage that happened, 2 of May, 3 of May, 4 of May. That one is solar radiation, right? And the consumption and the delivery. But more important, you need to know what is going to happen the next day and the day before and the day before to determine how much current you are going to keep or how much current you are going to storage in your battery. The prices of the battery, I make that work for the 2016, they were keeping down, and now they are getting a plateau. But anyway, Tesla, I quote this Tesla for my home. Even I used to work for Sony Battery, but I call, and that one was more or less the price that they quote me in the 2017. And this one was DC at that point. The quote was for DC, but they coupled myself. They will make a DC line themselves. That one for me was $7,000 for, I think, was 4 kilowatt hours. Then more or less was the price that they have here. Then they are coming, Sony can come down too, even though Sony do only AC systems, AC nanogrids. Tesla is doing more DC nanogrids. Then maybe nanogrids are ready for prime time because the renewables, there are many opportunities with that because they are intermittent. Some regulation, some tariff, peak demand, the energy is getting more expensive, and then you have to transport energy from one place to another one. Transmission line, we know for the fact that it's getting more and more expensive. And then nobody wants a transmission line in your backyard. Then all are possibilities. Then the technology is here, and I think it's very close to be affordable for everybody, and then I think the opportunity is there. Then that one is a shameless advertising of a book I have. It's going to come in very short. It's in my past life. I was working in reliability, and that one will come. Okay, that's it.
All right, thank you, Dr. Ginart. We got some time for Q&A, or at least Q. A will come.
Thanks. First, really good presentation. Enjoyed it. Can you talk a little bit about the batteries that are getting put inside of the home? So, Tesla has their battery packs that are going in there. Have they been used inside of a car for 500 cycles, and now they get moved into a home? And how much life is left? And then, how do you see the batteries inside of the home being used? Are they being used for emergency? Are they being used by the utility for, frequency management? I guess I'm just wondering, what is the additional wear and tear that's going to be on the battery? How often is it going to be used? And, are car batteries good choices for home?
Excellent question. And that book is related to that. I mean, even the GBTs, all the elements, they are no different than the tire. Then you are right. I mean, of course, not every battery is the same, but Tesla used lithium-ion cobalt. That is excellent for cars, very bad for stationary batteries. But Tesla have I don't want to talk bad about just, my gut feeling is they don't have too much life. Especially they use used batteries. They don't have, probably in the lab where we were testing lithium-ion cobalt, they die 5 years, 7 years. Even though in the road they are showing way more last time. The problem is the people is not using the electric car like it was predicted. That one is my take. Then taking that consideration apart, I don't think they will have the life they propose. Only lithium iron phosphate have the ability to last 10, 15 years for the experimental results. But you have Tesla backup. I hope they honor that. Then at least 3 years, the battery begin to reduce. I hope they replace you the battery. But yeah, my technical assessment is that one won't last more than 3-4 years more.
How about the the life of the lifetime expectancy using more traditional lead acid battery as the storage?
Yeah. Again, I believe that lead acid is extremely short life, right? But we say in power electronics, we say the same with silicon carbide and silicon. And silicon keep fighting back and getting better performance, and silicon carbide keep pushing and still it's expensive. Then when I was young, that was a long, long time ago, I have to change the battery of the car every year and a half. Now lead acid lasts 5 years. Then my gut feeling said that this lead acid cannot improve way more than that, but always is price related. Because you have to be willing to change, it lasts 5 years, and then you are willing to replace it. The company that put the batteries replace you the battery, you don't care. It's like a tire. You change the tire, and you keep going. Then technology, they don't have the life that lithium iron phosphate they have, but economically, maybe makes sense. What I don't believe is they will last 10 or 15 years. But they can, if you ask for warranty and the company is there and they will change it for you, at the end, it's irrelevant. Yes.
Yeah, sir.
So a few years ago, I was reading about a battery that's supposed to last for grid usage 20 years. It's got a kind of a typically around 2 volts, 2.4 volts, not the 4.2. Is that the battery type you're talking about?
Yes, I mean, it's Sony. The first that developed that battery was MIT with 123. And then they went bankrupt. It was a Chinese professor. They moved to China. And they are developing lithium ion now, phosphate in China. And Sony took it from Japan and they improved it to another level. Yeah, they call it, I don't remember the brand, but it's lithium iron phosphate. And the price was dropping down until they realized that it's better battery than lithium-ion cobalt. And last 15 years, depending on the use, like I showed several plots. If you deploy completely the battery, you have a number of cycles. Like a tire have a number of roads. If you drive only 5 miles, it's not the same that you drive 50 miles. Yeah, but then they are the potential, but the price didn't keep going down, even though the elements that they use is extremely cheap. They don't have any reason to don't go even lower.
Okay. So you kind of jogged my memory when you mentioned that. I know that originally the Nissan Leaf was supposed to use the LiFePO stuff, and I don't know what the reason is why they switched from that, but I imagine that has some major impact on the economies of scale.
In the economy scale, and for stationary they are very good, but they are extremely sensitive. I didn't talk about the bad thing. The bad thing is they have a range of temperature very narrow, that to be in a house is very good. In addition, they cannot blow because they have the energy density is a little bit low. We used to have the test that you put and you perform the lithium iron phosphate and don't get fire. They get hot, but don't get fire. But they have the problem that if you go outside of the temperature range, it's very bad. Maybe it was the price, maybe it was because in the car, you have to be able to drive. I was in a presentation in University of Texas, and one guy that was working for Volkswagen, they have an electric vehicle and they put it in Wisconsin or something like that. And the first time they run in a winter, they run 10 miles and they got stuck because it was so cold that you couldn't take out the energy from the battery. And then they have to design a hot electrode that they produce overheat the battery in order to get the energy out. Because the energy is there, but you cannot move because you cannot take it out.
That takes energy. No one lives in Wisconsin anyway, right? Next question.
Yeah, I have just put my 5 cents on the lead iron phosphate compared to the lithium cobalt. Actually, for storage, I think phosphate has a higher expectation than cobalt because you do not have a high expectation on the compact size or energy density, and the cost might be a little bit cheaper.
Yes.
So I have 2 questions. One is I want to know that the economic model of the storage system. And for example, if I buy a car and compare to a hybrid car, the battery pack costs about $8,000 more, and compare the gas price and drive distance I use for that car, it makes sense that if the car price or the gas price exceed $4 or 4.5, and then I can make money compared to the lifetime I use that battery and how much I can save from the gas. So my first question is, what do you expect the economic model for the energy storage system? When will it make profit? The second question is, we always talk about earth friendly or trying to be environmental friendly, but after the end of life of the batteries, what's the best way, or what do you expect the best way to be environmental friendly, to recycle them and reuse them?
Let me start from the second question. As far as I know, for example, lithium iron phosphate is very friendly because lithium is somewhat, and is the most, but even some people take lithium, right? I mean, then that one is not so aggressive to the environment. Iron and phosphate somewhat, but it's 3 elements that they are not so environmental challenge like other ones could be. I don't know about cobalt, but then that one is the easy answer. I think this lead acid is way more challenge because lead is very harmful to the life and Earth in all the types. Then depends what type of energy you use, then the battery could be less friendly to the environment or more friendly. From the first question, like in all the invention, you never know how it's going to pull out at the time. No doubt that battery is expensive and difficult. But the history of zoning, that I don't work anymore for them, is beautiful because the guy that created was in the storage garage. And then at that time, in Germany, they were asking and giving money to put the solar panels. At the point that in the summer of 2000 something, Germany have all the energy from solar. And that one raised many questions. One was, what happened if the solar pull out, one inverter pull out and we lose all the stuff? Then we need batteries. Then, in any way, we have too much solar. Then they said, oh, I won't pay more because German is very controlled society. They said, okay, we put the money, I give you the money to put the solar. Now I am going to pay you only 7 euros for the energy that you sell to me. But if you want to buy to me, I will sell you for 25. Nobody can realize that that one will happen. But this guy in the garage realized that, and I said, oh, instead to sell it to 7 during the day, and I keep it and use it in the night, at night, instead to pay the 25 to them, that is when I need it, is I have the storage, and Sonnen created. And then he find arbitrage, and he created a company that now is doing pretty well. But didn't stop there. Somebody, I don't know who was, have even more brilliant solution. That is the reason the economics is very murky. He realized, hey, one moment, we are producing energy, we are utility. And then it's not fair that we produce energy, we have the same rates that like a world consumer. Now we are utility. And Sonnen was declared Sonnen community. Sonnen is utility. They can buy rate to the wholesale. Maybe you don't know that one, but the utilities don't buy energy at the same price that you buy. They have a wholesale market like you can buy, and then Sonnen in Germany, they can buy whole energy. Then not only they can storage, but they can buy the energy cheaper. And they realize that they can sell energy. And then they have the solar community that they sell energy cheaper. And then right now is the most growing utility in Germany. From stuff that you never imagined, they will make money. And then that one is the most important source of fund of revenue that they have. Is Sonnen community. That means because they are utility now. In the United States, more difficult than what they do in Sonnen to survive. They go to the builders and they sign contract. And when you are building the home, you include the battery package there. Then they get preference because some areas that they are very restricted to building, you say you are environmental friendly, and then they give you the permit. And even though expensive, over the top of the price of the home, you even don't notice. Then there are many ways that you can deal with economy issues that is not obvious at the moment. But you are right. If you go dollar per dollar, sometimes it's difficult. But even though I was considered that myself, put Tesla, that when they offered to me $7,000 in my solar panel and pay in 2.3% interest, and then that one was like a $10 a month. Then even for myself was making sense.
All right, I guess for your cost model, you should be watching the Saudi Khashoggi murder issue very closely because it has a big play on your economics, I think, at the $4 price.
I was just going to say that the utilities have a lot of different models. So, for example, for some of the commercial places, they will charge you based on the maximum use that you pay, and that
time of the day. But they have.
Well, it's the peak shifting and load shifting. So that higher rate becomes really expensive, and so to avoid getting moved up to that higher rate for the whole month, you'll see gas stations and commercial places put in these batteries so that they will always stay below that limit. And then for residential, there are different tiers that go up to 45 cents per kilowatt hour, and the lowest rate is like 9 cents per kilowatt hour. So there might be a benefit to use battery to offset that 45 cents per kilowatt hour. And so, I mean, it's, or the utilities will take a look at, what is the cost of putting in new transmission lines to service a particular area. But if I can put some storage in place so that I don't have to put the transmission lines in, then, they might give a special rate to people to put battery in. So there are a lot of different financial models that the utilities will use, and
in many states, still, yeah, you are right. It's a very good answer. In many states, still they have the flat, but depends. In California, they are putting different rate, the peak demand, and then that one, all this stuff that you cannot foresee at the beginning can make a difference in the price of the system.
I had a question regarding the transformer-less inverters. So are they more expensive or?
No, they are way more cheaper. The problem is you have to pass the certification I show, I don't remember the number, that you cannot have ground current more than certain specification. And the ground current happens between the capacitance. I simplify that stuff, but the capacitance has to do even with the case that you use, because capacitance is everything that two plates parallel are capacitance. Right? Then when you make the inverter, it's very difficult, even though you make some calculation. When I was designing inverter, what I did was I assumed a flat inverter, I put all the area, I multiply by 2, and I said, okay, that one is the capacity of my inverter. I put some location, I said how much current I am going to drain to the ground. And then you have ways to, and then there are systems to measure that. But it's way more cheaper because the only competition, I show, let me see if I can go very quickly. There a plot that they make that comparison. I didn't stop there because it's too much information. But then, because it's lighter, and unfortunately, when you massify the product, at the end it's material. Because everything is material at the end. When you put it in the stuff that weighs less, is the stuff that is cheaper. Then you can see how transformerless is the weight is way less, like 3 times less than the transformer type, very close to the high frequency. This one is the high frequency. Very similar what I show you, the only thing, when you want to be bidirectional, you change the diode by MOSFET or IGBTs, and the efficiency is superior because you don't have one element, you don't have a transformer. Very basic, very simple. Then it's way more efficient, less weight, less material, and then it's less cost.
So these companies like SMA, SolarEdge, are they making these kind of transformers?
Yes. Actually, I worked for SolarMax in Europe some time ago, and it's bankruptcy now. SMA, SolarMax was the first to do transformerless inverter in residential area and commercial area. SMA was second or third, and then they grow because they were the German company, and then they grow. All transformers that you go in residential, in battery storage, still they use transformer. I was working in the first inverter, transformerless. Like my friend Sharisha said, it's the same, but you have to change the firmware. But too many people don't know that. Then you have to change the firmware, and you have to adapt some stuff. I was going to explain how you can do the transformerless, but it's too many details. But then, yes, answering your question, all the big companies nowadays, they are transformerless.
Any other questions? Actually, I was kind of wondering, since we were on the topic of the economics and all this, when I think of any energy storage, particularly residential scale, I kind of think of 2 primary applications, right? One is the actual providing, supplementing energy when you're, say, your main source of your nanogrid, your microgrid is not available, right? PV at night or whatever. But then the other one is peak shaving, right? Where you can actually intentionally size your entire infrastructure to kind of the steady state average instead of the absolute max, and just use the localized energy storage to handle the peaks. Yes. Which, assuming you're not operating at peak load too often. I was wondering if you could comment on that, especially from the economic standpoint, kind of the economic analysis of those two different uses of localized energy storage.
That one is very interesting, and you are exactly in the right point. I used to have my conversation with my German friends, and then always they said, how is, Antonio, the rate in the United States for the peak shaving? I said, United States is not like Germany. Every state put their own rules, and not only, every state has 25 utilities, and every utility charge whatever they want. Then, okay, 1 week later, Antonio, can you tell me how much they charge for the peak shaving in the United States? Okay, I stopped to answer because, yes, then depends how much we are going to charge for the peak shaving. That one will make a lot of sense. When zoning started, yes, in the commercial, that one was the main goal. But Georgia, for example, don't want to charge for the peak. And still what you are charging in California is not representative of the price that the peak shaving have, because sometimes the utility has to pay 25 times for that energy in that summer or that winter, especially the summer, to provide the energy to you. That is the reason sometimes they cut you. And they don't say why, but they cut you because they don't want to pay the 25 because you are not going to get it. But it's more complicated than that. In order to charge you for the peak shaving, you know how they charge for the power that you go? One guy go every month, and then they see, oh, this guy consumes so many kilowatts. Well, I'm trying to say you have to have the smart meter. Not everybody has a smart meter. You have to, for every minute, you have to get the reading, and then now you know how much you charge in the peak shaving, and then now they can, but that one needs an infrastructure again. Very large infrastructure that when we have it, I think we are going that way because it's not the analog type that don't communicate it with the Internet of Things that we are right now. It's easy to imagine that everybody will have minute by minute how much, or at least every 5 minutes, how much you are that. And at that moment, the utility will say, okay, I don't want to pay the 25 times that I was paying. Please, can you share with me that price?
All right, thank you. Oh, and we'll take a final question here.
I just wanted to comment in Sunnyvale here. As far as I know, PG&E has rolled out smart meters for everybody, like about 5 years or 10 years ago.
Yeah, probably. Like
yeah. But I thought that was true in all of California, even though there's several different utilities.
But maybe even if for all California, like you are saying, I don't know if it's in all the California, but still it's not in all United States.
Right.
I mean, probably will be 3 or more for a state that they, even if it's all Californian, and I doubt it, because maybe it's the all metropolitan cities of California. There are places that they don't measure, they don't go nobody there because it's so expensive, they don't have internet.
Okay. Okay, yeah, it's very complicated, like you said.
That one is, but I foresee in the future that everybody will have smart meters. Yeah, it will be like you have a color TV, something like that, or cell phones. I mean, yes, but not.
So,
huh? You will laugh about me, but for me I was weird when I began to see the color TV.
So I'll just quickly, as a result, PG&E gives us all these choices. We can choose the EV rate, like or E6. Yeah, smart meter first.
All right, let's give Dr. Ginart one more big hand. Thank you very much. And just to make your time worth it, everything else, we have this token of our appreciation. I'd like to present to you on behalf of the chapter. Thank you very much. We'll take a gratuitous picture here. Thank you. All right. Thank you very much.